We've been talking for a while now about how some problems can be solved in polynomial time, while others seem to require some kind of brute force search, which typically takes exponential time. In this unit, we're going to talk about the P versus NP question, which is how theoretical computer science has been struggling with this issue. And it is still really the largest open question in theoretical computer science, and many consider it one of the largest open questions in all of mathematics. The idea of P versus NP, you can think of it as finding solutions versus checking them. If you recall the Hamiltonian path problem, I give you a big network, a big graph with n nodes, and the question is whether you can tour the graph, moving along its edges and visiting each node exactly once. Well, we don't know a fast way to find such a tour or even to tell whether one exists, but it's certainly true that if you show me one, or God gives me one in a dream, or I trip over one on the sidewalk, I can check to see if it works. That's easy. Just check that it moves in a legal manner along the edges of the graph and that it does indeed visit each vertex. So this problem has an interesting property that solutions are easy to check. Specifically, a proposed solution can be checked in polynomial time to see if it works, even though it's not so clear how to find one. This is what P and NP are about. P is the class of all problems that can be solved in polynomial time. NP is a larger class of problems where a proposed solution can be checked in polynomial time. Now, you might think that the N in NP stands for none, and that NP is everything outside P, that it's the complement of P. That's not true. It's a larger set that includes P. And in fact, the N stands for non-deterministic, which doesn't mean what you probably think it means. It doesn't actually have anything to do with probability or randomness. It's more something that comes from the early history of theoretical computer science. The idea of a non-deterministic computer is one that can make guesses, and then it can check to see if its guesses worked out. So P includes, as we've already seen, the Eulerian path problem, because remember, that's telling whether we can cross each edge exactly once. We can solve that in polynomial time just by checking to see if each vertex has an odd or even number of edges on it. P also certainly includes problems like multiplication, because we know how to multiply two n-digit numbers and get the result in an amount of time which is polynomial in n. Now, NP includes, as we just saw, the Hamiltonian path problem. A little bit of a caveat here. Strictly speaking, NP is a class of decision problems, yes or no questions. Is there a Hamiltonian path in your favorite graph or not? The actual search problem of, oh good, there is, well show it to me, is closely related to NP, but as we'll see, it kind of make things simpler just to think in terms of yes or no questions, or decision problems as they're called. So notice that I've drawn this diagram so that NP is bigger than P. Well, we know that NP includes P because if we can find solutions reliably, we can also confirm them by checking that our program works. But we believe that there are many problems, including Hamiltonian path, where solutions are easy to check but hard to find. In other words, we believe that NP is a larger class of problems than P. But we don't actually know this. We don't know for sure, for instance, that there isn't a polynomial time algorithm for Hamiltonian path, the same way there is one for Eulerian path. In order to sharpen this question, in order to raise the stakes in a way that you'll see in a moment, we're going to focus on particular problems that have a property called NP-completeness. At first, this property will be kind of mysterious. So remember from earlier in the course, when we talked about translations or reductions from one problem to another. Let's say this again a little more precisely. Suppose I have a problem A and another problem B, and I want you to remember that a problem here means a whole class of problems, a type of question. We don't mean a problem like, does this graph have a Hamiltonian path? We mean the general question of, does any graph I describe to you, does it have a Hamiltonian path? So, we'll say that A can be reduced to B, and we'll write A as less than or equal to B, if there is a polynomial time algorithm which can translate or transform any instance of A, any example of A, like a particular graph, to an instance of B, so that the answer yes or no, is there a whatever it is, stays the same. The answer to A is yes if and only if the answer to that example of B is yes. Now, remember our example from earlier on where we took the bipartite matching problem from our heterosexual dating service, and we translated it into max flow problems. And in this case, the translation algorithm was extremely simple. All we had to do was add a source over here and a destination over there and draw a bunch of arrows. That was it. Hardly any computation at all. This is pretty standard in what we mean by a reduction. Of course, sometimes it's more complicated than that, but the reduction is not trying to solve the problem. It's only trying to transform the problem from one format or language, if you like, to another. It's a little bit like a translator at an embassy. If one general asks another general through a translator, "Are you willing to sign the peace treaty?" Well, the translator isn't supposed to think about it and solve the problem and say, "Why, yes, I will," or "No, we're going to attack you." The translator is simply supposed to create a faithful transformation of that question in the other language. And that's what reductions are doing as well. Now, here's the surprising fact. There are problems in NP, which I'll call B, so that every other problem in NP can be reduced to them. Problems B, so that for all problems A in NP, any problem where solutions can be checked in polynomial time can be translated into this problem B. What in the world does that mean? That means that B is somehow such a general problem that we can express nearly any other kind of solution checking problem in terms of B. So think about it. Think about all the things that you might be trying to find or fit or optimize where you could check it. I give you a map and ask you whether you can color it with only 3 colors. Might be hard to find, but it's easy to check. I tell you, here's a microchip. I want you to lay out the transistors so that the total amount of wiring is less than a certain number of centimeters. Again, might be hard to find, but easy to check. Even a mathematical proof. If I give you a mathematical proof written in some formal axiomatic system, well, mathematicians like to think that proofs are hard to find because we need to be creative. And yet the whole point of formal proofs is that they can be checked to see if each line of reasoning follows from the previous lines of reasoning and from the axioms. So if B is one of these NP-complete problems, it means that it can somehow talk about any of these things. Map colorings, chip layouts, mathematical proofs. It means that B is somehow very powerful in general in what it can talk about. Now, at the moment, it's not clear that there are any such problems, right? Maybe this is just pie in the sky. But suppose there were. Well, remember that if A can be reduced to B, then if A is hard, B must be hard too, because otherwise you could solve A easily by translating it to B and using your miraculous algorithm for B. So this means that this problem B, to which every other problem in NP can be reduced, must be one of the hardest problems in NP. It lies at the top of the class NP. What this means is that this question of P versus NP Can things that are easy to check, are they also always easy to find? We can focus on an NP-complete problem and ask just about this one, because if any NP-complete problem can be solved in polynomial time, they all can be, because it can express all of them. But that would mean that P equals NP, and that anything which can be checked is also easy to find. Turning that around, if P and NP are different, if indeed there are problems in NP which cannot be solved in polynomial time, then in particular, any NP-complete problem cannot be solved in polynomial time. So, if you'll grant me for a moment that there is such a thing as an NP-complete problem, then it's kind of all or nothing. Either that problem can be solved in polynomial time, but then every problem in NP can be solved in polynomial time, and P and NP are the same. Or P and NP are different, and that problem really requires more than polynomial time. Well, here's a preview. Hamiltonian path is NP-complete. At this point, that should be totally mysterious to you. It's really not clear how a little puzzle about touring through all the nodes of a graph could somehow express any other search or optimization problem that we might care to name. But I will prove to you later on that this is so. So stay tuned.